In this lesson, we are going to look at what a limit is and look at it in kind of an intuitive way and how we can estimate limits algebraically. So we'll start by looking at graphs. So the first thing we want to look at is what does it mean for a graph to be continuous? And we're going to do this today in a very intuitive way. Later in the course, we will be going back and doing continuity in a more formal way where we use the definition of limit to help us define what it means to truly be continuous. Okay, so when we're looking at continuity, we're looking at a function being continuous or discontinuous. Basically, any continuous function continues. It goes on and on and on. There are no holes, there are no breaks, there are no vertical asymptotes. There's nothing that's separating the function. The function goes through every point, every x value on its way, along its merry way as it heads off for positive and to negative infinity. So we would call a function that looks like this continuous over the real numbers. Some functions are continuous, but continuous over a restricted domain. For example, radical y equals radical x is continuous starting at x equals 0, but it does not exist before that. Okay? So what if a function is not continuous? So we're going to look at a few different ways a function can be discontinuous. So our first kind of discontinuous function, we might have a little hole in the function. We call this a removable discontinuity. So this is the type of function where you have, the function pretty much is continuing most of the way, but there's one point at which it just stops existing for a moment. That is a removable discontinuity. We may have a different kind of discontinuity that's called a jumping discontinuity, where a function continues for a while, it's continuous for a while, and then at one point it stops, it goes from being where it was to being somewhere else. So the y values change dramatically in a way where we can't just continue the function. We call this a jumping or discontinuity. What else could happen? We could have something where we have like y equals tan x, or tan x that's been moved up slightly. And we have vertical asymptotes. A vertical asymptote can also be called an essential discontinuity. So these are vertical asymptote or essential discontinuity. Okay, so there's a lot of different ways we can be discontinuous. Most of the functions we've seen are continuous. The ones where we're likely to have discontinuity are things like rational functions. We may have issues when we take radicals. We may have issues with things like tangent that don't exist everywhere. Okay? So what does it mean for a function to be defined? Okay, at a point. Okay. So, okay, f of x is defined at x equals a if f of a exists. Okay, and in order to be a function, of course, we have to have an f of a. It has to be some definite f of a. Okay, so for example, we could have, let's look at two very similar functions. So if we have a function like this, and at 3 we have a hole or a removable discontinuity. Okay, so here at x equals 3, f of x is undefined. It's not defined. There's no value of f at 3, of f of 3. We don't know. It does not exist. So we could, however, have a function that's similar, where we also have a hole at x equals 3, but we put a point somewhere else here. So there's this point, so this is f of 3 is up here instead of right there in the middle of the function. So here we have at x equals 3, f of x is discontinuous, but it is defined. So if there is a value at a point, then it's defined at this point. If it doesn't have to be continuous at the point, but it does have to be defined. It is defined at this point. It's defined, so this f of x on the right is defined everywhere. The function on the left is defined everywhere except for x equals 3. Okay. So, what is a limit? A limit, the limit of a function as we approach a point is where the function is getting to. It is not the same as what the function is, it is where the function is getting to. The function has to be approaching the same point from both sides. Okay, so we define the limit as x approaches a of f of x equals L. So this is not what the function is at x equals a, at that point a. It is where the function is going. So for example, it needs to approach it from both sides. The y value f of x approaches as x approaches a from both sides. It's really important that it has to be the same from both sides. If you have a jumping discontinuity, then that limit doesn't exist. Okay? So let's look at one example where we don't have a jumping discontinuity. So let's take a lovely looking function here and let's put in a little hole. And this hole is at, let's say it's at 2, and let's make that a 3. Okay, so what we would say here is the limit, so the point here, the little hole that's missing is at the point 2 comma 3. So the limit as x approaches 2 of f of x is equal to 3. Okay, if this is our graph of f of x. So the limit as x approaches 2, as we're going along this function towards 2 in both directions, is 3. We're heading for 3 even though the value of that function doesn't exist. Even if we put a point like up here at 5, the limit as we approach 2 is still 3 because we are heading for 3. It's not about where we get to, it's about where we are going as we approach the number. Okay? So what would we say about a jumping discontinuity? Well, let's say we have a similar situation right here. We have our 2, we have our 3, and then we jump up to 5 and head off from there. Okay, so what can we say about this function? Well, we can think about two different things. So we can think about what's happening as we head from the left. So that yellow arrow is what's happening as we're approaching the function from the left. Well, we are heading for the point. As we're heading towards 2, we're heading for the y value of 3. So we would say the limit as x approaches 2 minus. So why minus? Because we're coming from the negative x direction. So it's not which direction you're going, it's which direction you are coming from. So the limit as x approaches 2 minus, or the limit as x approaches 2 from below of f of x And let's label this f of x just to be super clear. Okay. So the limit as x approaches 2 minus of f of x equals 3. So this is our yellow coming from the yellow direction. Okay. So now if we're coming from above, let's swap colors. We're going this way. We're looking at what's happening when we're coming from the right-hand side. So we say the limit as x approaches 2 plus, so as x approaches 2 from above of f of x equals 5. Okay, so this is our blue one. So we can call this one right here can be called the limit from below, or the left-hand limit. This one can become called the limit from above, or the right-hand limit. And I would read this, the limit as x approaches 2 from above. Okay? So, and I will write the limit as x approaches 2 from below, and the limit as x approaches 2 from above. And that's how you would refer to that little thing. Okay? So we've done our two. We would call these the left hand and the right hand limit, but what we can notice here is that they are different. So 3 and 5 are not the same. So if the two limits from the two different sides are different, the limit as x approaches 2 of f of x does not exist. Okay? So this is our conclusion, is that if our left-handed and right-handed limits are not equal, the limit doesn't exist. It's okay if we're going to a point and the point is different, but if we're heading for different points from different directions, the limit doesn't exist. Okay, so let's look at a couple of examples. Okay, so let's look at one that is a graphical example, and then we'll start to look at what do we do algebraically. If we're looking in a very intuitive way, what can we do algebraically? So we have our x, we have our f of x, and we have a function that's going, and it's got a wee hole here. It's going to keep going. Let's make that 3, make that 2. Okay, and let's say at 3, f of 3 is equal to 2. Okay, so f of x is defined for all x element of R. So we have this, we're saying this function is defined for all x relevant of R. F of 3 equals 1. So at 3, the function is equal to 1. So what we can say is the limit as x approaches 3 of f of x, well, we're not really heading for 1. That's just a little bit of a jump that's happened just at that one point. We're heading for 2. So the limit as x approaches 3 of f of x, and we're heading the same way in both directions. We're heading for that same point. So the limit is equal to 2. So it is possible for the limit of a function to be different from the value of the function at that point. This is the value of the function. This is the limit of the function. The value is where it gets to, the limit is where it's going. Okay? So how would we deal with an algebraic limit? Well, to start out with, let's see if we can estimate it. Okay? So estimating a limit. So what we can do is, let's say we want to estimate the limit as x approaches minus 3 of x squared minus 9 over x plus 3. Okay, we want to see what that limit is. So you notice if we plug in minus 3, we get 0 over 0. That doesn't tell us what's happening at that point, or what is the number that we are approaching. So let's make a table and calculate some values and see if we can figure out what y values we would be approaching for f of x equals x squared minus 9 over x plus 3. Okay, so we're going to pick some values that get close to minus 3 from below and close to minus 3 from above. So generally, we can start with like a minus 3.1, maybe a minus 3.01, minus 3.001. These are from below. These are slightly smaller. Minus 3 we know will be undefined, or what we would call here indeterminate. 0 over 0 we consider to be generally indeterminate. There might be something we could figure out about that. So slightly bigger than minus 3 would be negative 2.999, 0.001 above it, negative 2.99, negative 2.9. Okay, so when I plug these into our function, so negative 3.1 squared minus 9 divided by negative 3.1 plus 3, I get negative 6.1 approximately. Here, I get negative 6.01, negative 6.001. Here, I get negative 5.99, plug it into your calculator, square it, subtract 9, divide your answer by that number plus 3. Here I get negative 5.99 and negative 5.9. We can see right here, the closer and closer we get to minus 3, the closer and closer our y values are getting to minus 6. So it's really, really close to minus 6. So our estimate, okay, and it's a pretty reasonably good estimate, is that the limit as x approaches minus 3 of x squared minus 9 over x plus 3 equals negative 6. Because we can see where that function is, where the y values are going to. And remember, your answer to a limit is always going to be, what are the y values approaching? We give you what x values you have, what are the y values going towards? Okay. And you can do similar things with other questions. Okay. So hopefully that gives you an idea of how to do some estimating. The last thing that we're going to take a look at is, what do we do when there is no limit? When is there no limit? Well, let's see. Okay. If the expression gets infinitely large. So what might we have here? Well, if we're trying to take the limit as x approaches 0 of 1 over x, the closer and closer we get to 0, we're just getting bigger and bigger and bigger and bigger. And it's going to be different when we're heading from the bottom or from the top. Okay? So that's one that is going to be slightly different depending on what. And there are also going to be some issues if you have functions that don't quite work out. So if you're trying to take a function like, so if the expression gets infinitely large, or when the expression approaches more than one value, or doesn't exist everywhere. So an example of that one would be the limit as x approaches infinity, if we just keep getting bigger and bigger, of negative 1 to the power of x. Okay, so that doesn't exist because -1 to a positive to an even power will be 1, and -1 to an odd power will be -1, and -1 to any power that involves an even root is not going to exist. So there can be some problems there. So any rational power, some of the rational powers are not going to work very well.